Assalamualaikum warahmatullahi wabarakatuh. We are from Group 3 and we will be presenting our mini project for neural network titled Predictive Maintenance for HVAC Systems in a Commercial Building. So predictive maintenance helps to ensure the optimal performance of HVAC systems in commercial buildings. HVAC systems are responsible for maintaining a comfortable indoor environment by regulating temperature, humidity, and air quality. However, these systems are susceptible to faults and inefficiencies that can disrupt the operations and increase energy consumption. So with advanced analytical model, we aim to develop a proactive maintenance strategy that improves equipment reliability, minimizes downtime, optimizes energy consumption, and enhances occupant comfort. There are two objectives for our case study, which is firstly to build a predictive maintenance model that can analyze real-time and historical data collected from the HVAC system. Next is to identify patterns, anomalies, and potential faults in the system. So the data that we use contain 11 variables from the Mendeley data, which focuses on predictive maintenance of HVAC systems in a commercial building. The variables in the dataset can be categorized into three sections, which is temperature, humidity, and fan. So the first variable is return air temperature, which is the temperature of the air being returned to the HVAC system. Next is the supply air temperature, which is the temperature of the air supplied by the HVAC system into the structure. Next is the outdoor air temperature, which is the temperature of the outdoor air. And then the return air set point temperature, which is the air temperature set point for the return air. And lastly is the humidifier saturation temperature, which is the achromatism temperature in the humidifier. And then under humidity, that is return air humidity, which is a variable for relative moisture of the air being returned to the HVAC system. And then the supply air humidity, which is the relative moisture of the air being supplied by the HVAC system. And then lastly is outdoor air humidity, which is the relative moisture of the outdoor air. And then there is fan power in kilowatt, which is the power needed by the suckers in the HVAC system. And then there is fan energy in kilowatts per hour, which is the energy needed by the suckers in the HVAC system over a specific period. And then lastly, the 11th variable is an additional variable that we added, which is maintenance needs. This variable represents whether the maintenance is needed or not, where 1 equals to needed and 0 equals to not needed. However, we don't really utilize the exact data from the provided dataset. Instead, we create a dummy dataset with the variables in the Mendeley data to fulfill out the case study requirement that now consists of 132 instances. So this is a simplified flowchart from our report.
Next, step-by-step learning and analysis. First step, we collect data from sensor and automation system of HVAC system. Second step, we clean, reprocess, and transform the collected raw data into the structure forms. Third, we split the collected data into training and test set. Fourth, we select the feature variable, define the input parameter, and identify capable feature variable to improve the anomaly detected performance. Fifth, build and train the ANN model using the training data and ANN. Develop and train the model to capture nonlinear relationship among features. 6. Test ANN model performance. Evaluate the ANN model's performance using the testing data and calculate performance metrics such mean absolute error and mean squared error. 7. Hyperparameter optimization. We conduct hyperparameter optimization to enhance the ANN model performance. The next step, we evaluate the importance of each feature by weighting them differently to assess how much they impact the model performance. Lastly, test the model performance on real-time data and fine-tune the model as needed. Next, how analysis is conducted. First, using the various attributes related to temperature, humidity, set point, and fan power consumption. The goal is discover the connection between attribute and maintenance requirement using multi-layer perceptron model. Second, the pre-processing process, handle a missing value, outlier, and inconsistent in the models. The data exploration is understand the distribution, correlation, and pattern in the data. Finally, MLP algorithm training and testing. We split the data set, train MLP model on training data, evaluate on testing data. The evaluation metric that we use is the correlation coefficients, mean absolute error, root mean squared error.
Findings, which is I will show at WECA Explorer tools, but I just want to show that this is a brief view of our findings. And this is summary, data accuracy by class, and the mean absolute error, and also all the sigmoid knot. So I will show it in the WECA environment. Our output that have been run in WECA tools. So I will show a brief how we run it. So first we process the data as what have mentioned by the other members regarding of how the analysis works. So we have to process the data and then make sure the data can be useful for the model to develop. So in the classify tab here, we choose multi-layer perceptron here. So after we choosing that, we use training set, and then our target class which should be maintenance needs, and then we click start, and then this will come up. This is our classifier output that we have run just now, and then I will show the overall accuracy, which is firstly that our MLP classifier have achieved a correctly overall accuracy, which is about 81.82% on the training set. That means it demonstrating the correctly classified instances. So this means that these models have a potential to make accurate prediction. And there's a couple statistic which is show a moderate level of agreement between the predicted and the actual classes. And next, when looking at the class-specific performance, we observe that these models show a reasonably good result for both classes, which is class 0 is for no maintenance needs, and class 1 is for maintenance needs. So the true positive rate, which is achieved about 80.4%, while class 1 achieved 82.9%. That this indicate that these models actually have the ability to identify the instances belonging to each class effectively based on their true positive rate. And then next, we've found here that there's a mean absolute error, which is MAE, was 0.3225, that representing the average magnitude of the model's error. So the root mean square error, RMSE, is 0.4054, that providing a measure of the overall prediction error. Additionally, the relative axillary error and root relative square error reveal the average prediction relative error that range of the target variable. So here, as you can see. And then next here, as shown here, that we also have discovered, of course lah. Next, as you can see here, there's a sigmoid, and then we have 4 sigmoid knots and 2 output classes, which is maintenance 0 and class 0 and class 1. So each sigmoid knot has an input and weight, and a threshold that influence its activation. So notably here, there's sigmoid knot 2, and knot 3 had the most significant impact on the classification decision, that indicating their crucial role in the model's performance. So here, As you can see, this is compared to the rest, this one have more influential activation compared to the other seed mod. Okay. So overall, based on this compared result, we can confidently make a decision regarding our predictive maintenance strategy, which is this MLP model can have the promising performance in classifying maintenance that needs in the HVAC system, where it have also achieving the QC, which is the high one, and a balanced precision and true positive for both classes. This means that we can proactively identify that and we can address the maintenance requirements that next improving the system reliability and minimizing downtime. So I will show the MLP in their interface. So let's say this is what if we convert it into the interface GUI where we set it into 2. So as you can see here, we set the hidden layer, one hidden layer with 2 neurons. So as you can see, since we have class 0 and 1, so it targeting this class. So the layer is 0.2. Into the biggest one. So this is deep supply, D10, SP10, desaturation, the outdoor, RH supply, RH return, RH outdoor, energy and power. So this is the hidden layer and this is the 2 neuron and this is our target class, just our output.
Right, to continue on decision or business intelligence model, there are 6 stages. Firstly, data collection, where we have to gather relevant data from the HVAC system. On stage 2, which is data pre-processing, where we cleanse and pre-process the collected data from stage 1. Next is feature selection, where we need to analyze the collected data to identify the most informative feature for predicting maintenance need and optimizing energy efficiency. On stage 4, training and testing data, multi-layer perceptron or MLP is used for model development with optimized hyperparameter. In stage 5, model evaluation is to evaluate the trained model using the testing dataset. And the last stage, which is stage 6, interpretation of model decision, where we have to analyze the weight assigned to each input attribute in the trained model. Next, to conclude, our multi-layer perceptron classifier for HVAC system predictive maintenance demonstrate promising performance. This model accurately categorizes instances as no maintenance need or maintenance needs as indicated by its recall and precision rates. Focusing on utilizing advanced analytical models for predictive maintenance in HVAC systems allow us to proactively identify and address fault and inefficiencies, preventing major failure and ensuring smooth operation. By implementing the multi-layer perceptron algorithm in WECA to develop a predictive maintenance model, the prediction generated by the MLP model serves as a foundation for the decision business intelligence model. Implementing advanced analytical model and predictive maintenance approach overall provide a solid foundation for optimizing maintenance and energy efficiency in our HVAC system. It contributes to the cost effectiveness and smooth operation of our commercial building, allowing us to effectively prioritize resources and ensure optimal performance. That is all from us regarding our predictive maintenance for HVAC system in a commercial building. Thank you.